Hi, my name is Justin Dallas, and this is my semester project for EGR-214, Numerical Methods for Engineers, taught by Dr. Hans Chapman at Cape Fear Community College. This project is a MATLAB tutorial for Euler's method, and the related course is Calculus 2. The general formula for Euler's method is as follows. yi plus 1 equals yi plus h times the derivative of the function at the points xi, yi. yi plus 1 is the next estimated solution value, which would be plugged in for yi in the next step of the formula. Yi is, as it says, the current value for y. H is the interval steps between the different steps you're doing to approximate the line. And as I said earlier, f of xy is the value of the derivative at the current xy coordinates. To calculate the percentage error between the exact line and the approximate line that you're plotting, you would take the exact, subtract the approximate, and then divide by the exact and multiply by 100. This is the first textbook example for Euler's method. Provided is the step size of 0.1, where we must find the values at x equals 0.1, 0.2, and 0.3, and the function is also provided, which is as follows. Y prime plus 2y equals x to the third e to the negative 2x, with an initial value of y of 0 equals 1. The first step is you must rewrite the equation to as follows. Y prime equals negative 2y plus x to the third e to the negative 2x. Then what you must do is you plug it into the formula in the xy portion, multiply by your step size, and add your yo. Once you've completed that, you get your y1 amount. You plug that back in to the second part of the formula into y1, plug back in your function, plug y1 into the function, your x1, and then you get y2. You take your y2, you plug it back in, and this keeps repeating over and over for as many times as you need. And having a smaller step size makes your approximation much more exact, although Euler's method will never get you an exact answer. It will always approximate the line and never be exactly on the line. This is my analytical approach for textbook example 1. As you can see, even though we're only solving for 3 different points of x, using Euler's method to solve these functions can take quite a while and can use up quite a lot of paper. Even though it's a fairly easy algorithm to understand and apply, doing it over and over again can get very monotonous and very old, and that is why using the MATLAB approach is a more beneficial and fast way to solve these types of problems. This is my MATLAB approach to the first textbook example. My code for the MATLAB approach is as follows. At the beginning, you define your function. Next, you define your initial value. Then you define the time span at which you want to see the function over. The next, you define your step size. After that, you calculate how many steps you want to run. Then you initialize all the arrays, set initial values, and run the Euler's method loop for however many number of steps you specified to begin with. For me, it was 10, so I should get back 10 values. Next, you plot your line, and then it will spit out a table for you that will show your y and x coordinates through all 10 steps. Now, this is much faster than just doing it by hand. By hand, this would take 10-15 minutes. But doing this is much, much faster. And as you can tell, I mean, once you put in your step size and your function, it will immediately put out however many times or however many numbers you need up to whatever decimal value you're looking for. This is the second textbook example for Euler's method. This one's a bit more in depth than the first one, as you must find the derivative of the function first before you plug it into the formula. The derivative of the function y of t equals 1 plus 1 half e to the negative 4x minus 1 half e to the negative 2x is y prime equals 2 minus 4 to the negative e to the negative 4x minus 2y. Once you found your derivative, you plug it into the function along with your step size and initial values to find your first value, which in this is 0.9. Once you found that, you plug it back into the function again and keep doing it till you find your second number. Once you found your second number, in this case it's 0.852967995, you plug that back in to find your third value, and so on and so forth. Here it's went to the fifth step, so it's found 5 values. This one also plots the exact line and shows the error percentage between them. My MATLAB approach for this textbook example was a little bit more in depth than the first one, as the first one I was only plotting one line and I was only trying to find those values. Here I had to find the exact line, plot that line, and then plot my approximate line and find the error percentage between the two. In my code, I first set initial conditions, defined my step size, defined my function, and then my exact solution. I initialize all of my arrays, set my initial values, and then I ran the loop for 5 times. This time I decided to only output a table instead of a plot, as well, as this is just more simple and matches the example from the textbook much more closely. As you can see, I didn't put my decimal places to 8 places, but that's a lot of decimal places to be trying to add into this table. But everything came out correctly, and once I had my code input in, you could change the step size, number of steps, function, and have this solved in a couple minutes compared to 15, 20 minutes. My third textbook example is a slightly little more in depth than the last one, though kind of not. It just uses different step sizes to show that the approximation gets closer the smaller the step size you use. Here the function given is y prime equals negative 2y squared plus xy plus x squared with an initial value of y of 0 equals 1. The step size here is 0.1 or 0.05 or 0.025. The exact number in this solution is found using a method known as Runge-Kutta method, which can give you an even more exact number than Euler's method. For my MATLAB approach for textbook example 3, I was having trouble outputting all 3 step sizes to the same table in the same code. So I decided just to solve one equation and then go back and input in the other 2 step sizes to find those values. The exact value here is from me plotting the function and finding the y values at those times. I tried to solve it using Euler's method, but since they used the Runge-Kutta method to find the exact values, my exact values were never coming out the same as what they provided. So the best way to get exact values was to just plot the line and find the values at the times provided. Finally, this brings me to the benefits and uses of Euler's method. Euler's method is beneficial for the use of differential equations, as these are used to describe like natural real-world things that do not necessarily have a straightforward answer that you can just solve on a sheet of paper. These approximation algorithms, like Euler's method, are used to solve these complex real-world problems to find a solution. The problem with Euler's method is that its approximation never really gets close enough to be very useful in the real world. It has a much more academic value as it opens up your eyes to what it is that these approximation algorithms can do and how they can help you solve real world problems. Now, using Euler's method is much, much easier in MATLAB versus doing it on paper. On paper, trying to go past 5, 10 steps, you're going to be working for a while. Doing something like MATLAB, you can put it into a loop and it will loop for as many steps as you need and will output it in under 30 seconds. So I don't know if I could ever go back to doing it by hand after I've done it this way. So this is my project for Euler's method. Thank you for watching.